Now that we're done chapter 2, we're actually going to step back and look at chapter 1, because chapter 1 is about vectors. We've already talked about vectors in chapter 2, but it was pretty simple because we were talking about motion along a straight line. So it meant that really one direction was the positive direction and the opposite direction was the negative direction. It was a relatively simple treatment of vectors. In this chapter, we're going to learn a lot more about vectors, particularly how to add them properly because of the fact that we have to consider their direction. For our pre-lecture video, I want to concentrate on the graphical methods of adding and subtracting vectors. This means the type of method we might use that would employ a ruler and a protractor to get the correct magnitude and direction of the vector. This method is rather tedious, and we, in practicality, will probably seldom use it, but it does have a benefit because if we understand it, often we can sort of make general guesses about what the addition of two vectors might look like. We'll get a sense of it would point in this direction approximately and be about this big. And so that's the value in learning this. So just to review, when we talk about a scalar quantity is something that can be described just by a number. So examples of scalars are things like temperature, mass, speed is a scalar. Those are just a couple examples. A vector quantity has magnitude and direction. So some of the examples we've already done of vectors is velocity, displacement, and acceleration. And pretty soon we'll look at force in a future chapter, is another example of a vector. So when we're talking about a vector, what we really need to remember is that we don't just care about how big it is, but we want to know what direction it points. There's some notation that goes along with this as well. In our book, it's relatively easy for them to represent vectors because they'll represent them with a boldface and with an arrow over it. And so that becomes an issue because when we're writing vectors, we can't write in boldface. So we always want to be careful that we use the notation with this arrow on the top to denote and emphasize that we're thinking of a vector. And then if we were just thinking about the magnitude of it, which sometimes we write like this, with the absolute value signs around the vector, that means magnitude. In your book, because of the fact that they can use boldface and regular font or regular type, they can just denote the magnitude as the letter representing the vector, but not putting the arrow on top. Okay, so when we draw a vector, there are two things that we have to worry about. We have to worry about how long the vector is and also what direction it's pointing in. So here, when we're looking at this vector, the length indicates the magnitude of the vector. So if we were going to draw a vector and we were going to be very, very careful, we would probably use some sort of scale to represent the fact that, like, for instance, 1 centimeter might represent a certain magnitude, like maybe it represents 5 meters or something like that. But the length has to be sort of proportional. Longer vectors have a higher magnitude or bigger, and so forth. Then the direction is pretty important because it's at a certain angle, and we have to show that as well. So when we're drawing a vector, it is really important to draw it with the correct length to indicate its magnitude and then at the right angle to indicate its direction. Something else that I just want to make note of is this part of the vector, this end, is called the tail, and this end is called the head of the vector. These two vectors shown here are actually equal to each other because of the fact that they're parallel to each other. They have the same direction, and because they have the same length, they have the same magnitude and direction. And so these two vectors, A and A prime, are actually equal to each other. They don't have to be drawn on top of each other to be the same. This vector right here, because it points in the opposite direction, is the negative of vector A. So here, of course, you can see that the direction is pretty important because it makes the two vectors different. So the first way that we're going to add two vectors is we're going to use what we call the head to tail method. So let's suppose I have a vector A and a vector B. And I want to add those two vectors together. In fact, I'm going to say that this angle right here is 40 degrees. Now, the first thing that I'd want to say is you would actually want to use a ruler and a protractor to do this. I'm not going to use it right now. I'm going to just do my best to make these the same length and in the same direction. So what we do is in the head to tail method, we always start with the first vector. And we do have to draw it with the proper length and the proper direction. And in fact, we're sort of imagining when we draw it that we have this imaginary x and y axis that we're measuring the direction relative to the x-axis properly. Now in this picture I tried to show that vector A was just horizontal, and so it lies along the x-axis. So, and now we draw the second vector, but what we do is we draw it starting at the head of vector A, then we draw vector B. And that's why it's called the head to tail method. And again, when we're doing this, we're sort of imagining that there's another x and y axis here, and that this angle that we draw B at is the proper angle that it was indicated at relative to the x-axis. Now these are just two vectors, and so when I draw them, then the sum of them, A plus B, equals, let's call that vector C. The way that I find the sum of them is I go from then the tail of the first vector all the way to the head of the last vector, and this vector ends up being the sum of the two. And that is what we call the head to tail method. Now there's another method called the parallelogram method, and that's when we make a parallelogram using the two vectors. And so in this one, we put the two vectors tail to tail together with the proper magnitude and direction. And then what we do is on parallel to each vector, we draw the vector again with its proper magnitude and direction. So this is like vector A here. See, it's parallel to the first vector A. And then we do the same thing with vector B. Now maybe my parallelogram isn't perfect, but hopefully you get the idea. Then, in this case, when we're using the parallelogram method, the sum of the two vectors is found by the diagonal of the parallelogram, vector C. And I think if you go back to the previous example, you'll see that this does look pretty similar to our last example. If you have more than one vector, or two vectors that you want to add together, you can just use the head to tail method by continuing. So for example, Here we see I go A, and then I added B, and then I added C. And R is the sum of A plus B plus C. So we just continue with the head to tail method. If I want to subtract two vectors, if I do A minus B is just in the opposite direction from B. So we can kind of say I'm adding minus B instead of subtracting, just what we learned when we learned about negative numbers. So negative B will look like this. So A minus B would look like this. I'd have A, and then I'd have minus B. And we'll call this D. D is equal to A minus B. That's how we subtract two vectors, and I used the head to tail method there. So that's our summary for today. I just wanted to show you these graphical methods in the video so that we could spend a little bit more time in class doing the mathematical approach, which is what you're going to be using for the rest of this class. We will be using this vector addition, this knowledge in chapters all through the first semester as well as the second semester. So it's a really important skill to learn.